Hi, we are from group B7 and in this video we're going to explain experiment 1, the phase diagram of a two-component system. In this experiment, our objectives are to be able to explore the utilization of phase rule in explaining equilibrium stage between two components at specific temperature and to learn that the degree of freedom at eutectic point is 0 where the solution is completely solidified.
When a pure substance liquid compound is cooled, the temperature falls until it reaches the freezing point. Variation of temperature with time as it is allowed to cool is translated into a cooling curve of that pure liquid compound. Phase transitions occur at specific temperatures. For the time it takes for phase transition to happen, or in this case, freezing, the temperature of liquid remains constant. A temperature arrest happens. This is due to the energy lost during cooling is counteracted by the energy released by new bond formations in the substance. Thermal arrest happens when equilibrium is achieved. The relationship between the number of components, denoted by C, and the number of phase, denoted by P, can be described using the Gibbs phase rule in the equation as below. F equals to C minus P plus 2. The phase rule is a general principle governing PVT systems in thermodynamics equilibrium where F is the number of degrees of freedom, C is the number of components, and P is the number of phase. In an open system, the pressure variable is fixed, thus setting the number of variables in phase rule to 1. In a single component system, for solid or liquid phase, F equals to 1. Only 1 degree of freedom is allowed, which may be the temperature. Temperature can be varied without changing the phase. However, at freezing point, there are two phases coexisting in equilibrium, which are the liquid and solid phases. There is no degree of freedom, and variables such as temperature and pressure must be specific and fixed to allow both liquid and solid phase to exist together. This results in an invariant point in phase diagram. For a binary mixture cooling curve at a constant pressure system, region AB has one phase which is liquid mixture. Since F equals to 2, variables such as temperature and composition can be varied without changing its phase. At region BC, 3 phases coexist in equilibrium, namely liquid mixture, pure solid A, and pure solid B. Here, the F equals to 0. No variables can be changed. Lastly, at region CD, 2 phases exist which are solid and solid B. Here, F equals to 1. Either temperature or composition can be varied. The invariant point is the point once the temperature varies, only either the solid or liquid phase will exist. After the phase change, F becomes 1 and temperature can be varied without forming any new phase. The invariant point can also be set as the phase boundary, as it is the line where both solid and liquid phases coexist in equilibrium. Even the word invariant itself means constant. In this context, a constant equilibrium of both solid and liquid phases. Eutectic point is the point on a phase diagram where the maximum number of allowable phases are in equilibrium. When this point is reached, the temperature must remain constant until one of the phases disappear. A eutectic is an invariant point. The curves separating the fields of A plus liquid from liquid and B plus liquid from liquid are termed as liquidus curves. The horizontal line separating the fields of A plus liquid and B plus liquid from A plus B pure solid is termed the solidus. The point E, where the liquidus curves and solidus intersect, is termed as the eutectic point. At the eutectic point, in this two-component system, all 3 phases, which is liquid, crystals, or known as solid of A, and crystals of B, all exist in equilibrium. Note that the eutectic is the only point on the diagram where this is true. Since we are looking at a system at constant pressure, the phase rule in this case is F equals to C plus 1 minus P. The eutectic point is therefore an invariant point. If we change the composition of the liquid or the temperature, the number of phases will be reduced to 2.
Next is the experimental procedure. Firstly, based on the table 1.1, about 5 or 6 grams of the following samples were weighed. Each sample was then melted in a test tube by immersing the test tube in a beaker filled with hot water. The thermometer was fixed on the lid and was immersed in the test tube until the thermometer bulb is about 1.1/4 inches to 1/2 inches from the bottom of the test tube. The test tube was then removed from the beaker and it was held by the retort stand while it is cooled slowly to room temperature. The temperature was recorded to the nearest 0.1 degrees Celsius in a second interval. Once the temperature was recorded, the readings were plotted on a graph paper until the temperature of the sample reached 10 degrees below its freezing point, 25 degrees Celsius for 60% naphthalene and 35 degrees Celsius for 80% naphthalene respectively. When the horizontal eutectic point was not obtained, the sample was melted again until the temperature reached 50 degrees Celsius. The sample was let to cool down at room temperature. The sample was transferred into a bigger test tube for larger space. Once an acceptable cooling curve was obtained, the same sample was melted again to obtain the second curve. Once the sample reached room temperature, the thermometer was removed and cleaned using a small quantity of chloroform. The whole procedure was repeated using other samples according to table 1.1.
So these are our results. And these are the graphs and phase diagram which were plotted based on the data we obtained. The freezing points for naphthalene and p-dichlorobenzene are 79 degrees Celsius and 53.1 degrees Celsius respectively, both obtained from the cooling curve plotted. A phase diagram was constructed using data such as freezing points and sample compositions from cooling curves. The eutectic temperature is 28 degrees Celsius and eutectic composition is 26% naphthalene and 74% p-dichlorobenzene. Phase rule F equals to C minus P plus 1 in an open system is applied here to explain the equilibrium state between two components at specific temperature. There is no degree of freedom at the eutectic point, in which the solution has completely solidified. Undercooling may occur when there is no seed, crystals, or nucleus that induce crystallization.